Hi everybody, here's the next set of slides from last week. So this is a bit of a different turn here, but I think it's something that plays a fairly large role in what we do from a non-massage perspective. We need to understand how the body works to some degree when we're going to prescribe any stretching or strengthening, those sorts of things. And we call this kinesiology. Now, a few of you obviously are kins that will be listening to this. This is a very shortened version of what you may have taken, but I think it's you'll understand why it's important. So what is kinesiology? It is the study of human movement from the point of view of the physical sciences. This is our ability to look at what's occurring when a movement is happening. And that can be sports, or it can be work related in terms of movements that are required. And it's the breaking down of and looking at the movements themselves. It's also the study of the human body as a machine for the performance of work. And then, of course, understanding this stuff, it'll much more support your ability to improve the performance of patients. And again, when we use the word performance, one of the issues is whenever we hear that word, the first thing we think of is sports. Day-to-day things, ADLs and so forth, or job requirements, they're still performance, and they still need to be looked at from the perspective of that. So when we do a kinesiology or a kinesiological analysis, what we're doing is, we're trying to break it down. So I want to describe a bit, and this will explain kind of why we're taking this. So first we want to do is when we're doing an analysis of movement, we want to describe the motor skill performance. So first of all, what is the primary purpose of the skill? What movements are occurring and in what phase? What kind of classification is the skill that's being proposed? And what is the simultaneous sequential nature of the motion? So what exactly is happening when we consider what's required of the patient? The next thing we do is an anatomical analysis. So we look at what joints and what joint actions and segment motions occur in this task or performance. The muscle participation and form of contractions, eccentric, concentric, shortening, lengthening, inhibition, and so forth. Then the neuromuscular considerations, of course, would make sense because we're looking at the muscles. And then we look at the anatomical principles related to effective and safe performance. So how do we ensure that our client is doing it as effective as possible? And are they doing it in such a way that it will be safe for them? The next thing is the mechanical analysis. So this is what we look at is first the underlying mechanic objectives or objective. So what is it at the end of the day that needs to actually occur here? The next is the nature of forces causing or impeding motion. So if you think of things such as pushing or pulling, you can see the nature of forces that are required. What mechanical principles apply to the performance or action that's required? And when we talk about, look at the principles, which we're going to be talking about today, it's the violation of principles. So what applications of mechanical principles are being violated? So, once we understand the principles, how are they not being dealt with? Which is, the next part, which would say, what are the errors that are occurring in the action of the patient? So when we look sometimes at a performance requirement, when we ask our patient to show us their application of the performance or their interpretation of the performance, we might see that in fact they're not working the principles of movement appropriately, and therefore they're making errors, which of course can lead to further injury and so forth. And so when we think about the errors that might be happening, what are the sources of those errors, and then we move from there. The last is prescriptions for improvement of performance, and these will indicate how the performance should be changed so that the principles are no longer violated. So again, A, B, and most of C, we're breaking down what's being asked or what the performance is, and then throughout that, then we move into how can we create a better, more efficient, safer, and how do we avoid the violated principles that we're going to be learning here today to some degree. Now the analysis, what's the primary purpose of the skill? Why are they doing it? What's the requirement? And then from a classification point of view, independent living or work? Is it health and play? Is it near perfect performance, such as, an athlete that's being judged, such as a gymnast or a figure skater or something like that? And what is perfect, or what is what's the best that it needs to be done? When we look at the system for classification of motor skills, the posture, so maintaining good posture, movement for exercise and fitness, and we want to consider those. And then from a motion point of view, are they pushing or pulling external objects? Are they throwing something? Are they striking something like with a baseball bat on a baseball, or a tennis racket with a tennis ball? And are they doing something like kicking in terms of what's required? And what movement is occurring to one's own body? How is the body itself actually moving through these performances or tasks? When is the body, or is the body suspended and free of support at any given time? A different one is a swimmer, for example. Is the athlete, in this case the athlete, are they doing their performance suspended in water, which makes a bit of a difference to movements and when you're analyzing. The last one is receiving impact. So are they, something like martial arts, are they being thrown or are they landing onto a mat? So are they, what's happening there? And then receiving impact can also be, catching, trapping, or intercepting anything such as footballs, baseballs, and so forth. When we're talking about sequential nature of motion, I want you to have a look here of what's happening. So we can see just a basic standing long jump. This is how we need to break it down. So what position is the initiation of the movement to the start? Then we have the middle part when we're moving through the motion, and then how do we land? So we can see that there is a sequential nature here of the motions throughout this movement. And this is what we're analyzing, what's happening when and where. And if I were to get you just to sort of analyze to some degree on your own, start suggesting to yourself what movements are occurring at what joints, what muscles are working to have those actions occur, and so forth. So what joints are involved and what are their exact movements in the motor skill? Are any of these joints used to the limit of their range of motion? And of course, if there's limited range of motion generally, they may not be able to perform the full movement. Which muscles are responsible for the joint actions and what kind of contraction, concentric or eccentric is an example, and which neuromuscular mechanisms are likely to help or hinder the action. So what's being inhibited or what's being stimulated. The next is motion. So relative motion. If we look at sort of how that defines, motion is the act or process of changing place or position with respect to some reference object, whatever that may be. It is possible to at rest and be at rest and in motion at the same time. This is something that can occur. So when we look at relative to the differences in points, for example, sleeping in a plane, you're not moving, but the plane is moving. Right? Two joggers at the same speed, there's no motion comparing each other, but motion along the road itself if we compare it to the road. But when we look at the two athletes, there doesn't seem to be much at all. Translatory movement. So this is also known as linear motion. And there's two movements. It's called rectilinear versus curvilinear. Rectilinear is defined as a straight line progression of an object as a whole. For example, a child on a sled. Whereas curvilinear is a curved translator motion. So these are objects that move in a curved pathway, such as throwing a bowling ball. So we think about that, swinging a golf club, it's curvilinear in nature and so forth. Rotary or angular motions, these are typical of levers, wheels, and axles. The leg as a radius moving about a fixed point, the hip joint, when kicking a soccer ball. So what I'm breaking down here is all the various movements when you in fact are looking at the performance that the individual has to do. Again, whether that's sports or work. Within the context of those, we need to do some laws. And this sort of represents what we're looking at when we're breaking things down and looking at them. The first is Newton's law of motion. And it states, a body continues in its state of rest or of uniform motion unless an unbalanced force acts above it. In other words, an object at rest stays at rest. A moving object moves along a straight line and at a constant speed until acted upon by a force. Now that could be friction, right? Just your foot on the floor or skate on the ice, whatever it may be, or even gravity or air resistance. When we look at where this law kind of works, I want you to think about having to change velocity. So if you're stealing a base, well, what does the athlete have to do to avoid overrunning the base that they're running at? Sorry about that. I have to go and shut my cat up. So think about what has to happen when someone is running full tilt at a base, and what do they need to do in order to stop the motion that they've created? The other one is a car stops suddenly and we keep moving. And this is something to think about when we're looking at injuries, especially car accidents, where we look at the damage that can occur at the physical body, and this is what happens. That car is moving, let's say, for example, at 100 kilometers an hour, and you have a head-on collision. Everything in that car, even though the car is stopped profoundly with the impact, you will keep moving at 100 kilometers an hour. Now, of course, if you have a seatbelt on, that's going to prevent you from going very far, but you can imagine the damage that could do to physical structures if, in fact, that 100 kilometers an hour is going to be placed on the body. The property of an object that causes it to remain in its state of either rest or motion is called inertia. The greater the mass, the greater the inertia, and the greater the force needed to move or change the object. So again, when we think about this, if something is relatively heavy, it's going to take a lot more to get it moving, right? The next law we have to learn is the law of acceleration. So the law of acceleration states, the acceleration of an object is directly proportional to the force causing it, is in the same direction as the force, and is inversely proportional to the mass of the object. So if we think about pitching a baseball, the velocity of a pitched ball reflects the force with which it is thrown and moves in the direction of the line of force at the moment of release. So we'll take a moment here and think about what it's like to throw a baseball. You must be able to, when we think about, proportional to the force causing it, to overcome the mass of the baseball is not a huge amount. The baseball is relatively light. But of course, if one wants to throw a ball exceedingly fast, there are athletes out there that can throw a baseball 100 miles an hour, then think about what has to happen with the movement to cause that. So the amount of force with which it's thrown will result in a 100-mile-an-hour fastball. And where that fastball ends up in the strike zone, shall we say, is directly related to the release point in the athlete's hand at the point where they release the ball. So we've got to think about that, we had to create that force, and then we have the release point. Less force to stop a ball traveling at 5 meters per second than to stop a pitch of 50 meters per second. So again, for the law of acceleration, in order to change that ball, there has to be a force also created by the athlete who's the batter at the plate, who is swinging the bat. And when you add the two together, you can see where someone can hit a 400-foot home run, and because it's the combination of both the force of the ball's speed as it hits at the plate, and then the power that's created by the athlete who's swinging the baseball bat to make an impact there. So what in fact you're doing when you hit the ball, you're actually stopping it because it's coming at you 100 miles an hour. You have to create the force to stop the ball when it makes impact with the bat, and then of course then it's going to head in the other direction. So the mass of the ball is the measure of its inertia, and the greater the inertia, of course, the more force it takes to change the object's velocity. In other words, again, the thrown ball, the harder it's hit by the baseball bat, if you want to use inertia, the faster the ball is moving, the more that needs to be done from a force perspective with the baseball bat. The greater force has to change the velocity of the ball. Obviously, the velocity is traveling in a particular direction at a particular speed towards the plate, and then the bat makes the impact. And we have to take all that inertia that was created from the pitch and change it entirely to go to a different direction. So in other words, F equals ma. Force equals mass and acceleration. So the pitched ball, the ball has a mass. It has a particular acceleration to it that was created by the pitcher who threw the ball, and then the force that was created by the baseball bat equals that mass and that acceleration plus more in some cases. So we can see here that, I don't know why that changed in terms of formatting. That's very odd. Just give me a moment. So sorry, I can't change it here, but we can see here that we've got a golfer here that is going to hit a golf ball. And then, of course, we have the same golfer trying to move, rather than the golf ball, to some degree, is the truck. So a couple of questions here to ask in looking at this diagram. So how much force is required to move the golf ball when putting? Let's consider how much force would it take, to hit this golf ball and have it move forward. And the other thing, if we look at, the law of acceleration, the other thing we need to consider with the golfer is not only moving the golf ball, but of course how far the golf ball has to go. So how much force would it take to move that golf ball? How much force would it take this golfer to move the truck? In other words, comparing the golf ball to the truck, sufficient force must be applied for an acceleration to occur. So it's about creating the force, and depending on the mass that you have to move. The same force exerted on a larger mass produces a correspondingly smaller acceleration. If we use a comparison of a golf ball to a truck, it's likely that the golfer couldn't move the truck. He would not be able to create enough force against the mass of the truck himself. The next law is the law of reaction, and this states that for every action there is an equal and opposite reaction. So, for example, a book lying on a table exerts a downward force on that table. And because the book is stationary, another equal and opposite force must be acting on the book, which of course is the table itself, right? It's actually acting it, because without that table, that book would continue to move downwards towards the floor. So because of the first law, that we can now say that there's a balanced force system. So there is an equal force heading up at the book, meaning the table, as the book wants to travel down. Because they equal each other, the book just sits on the table, it doesn't go anywhere. Now we can apply that to when we're moving. So when we walk, the feet push back on the floor with the same magnitude as the floor pushes forward against the feet. So that's how we move forward. And the question I would ask you to get a sense of what happens here, even though we don't think about it, if I were to take and put you on a skating surface, how would that be in terms of being able to walk forward? You don't get the same pushback on ice. There's less friction. So therefore, it's harder to move forward because you don't have the opposite pushing against the foot. In other words, without this ability to have reaction, we can't move forward. This is why we use starting blocks when we're looking at 100-meter sprints. It provides this opposite force when the athlete initially pushes off at the starter's gun. So when we can see this picture here of a foot in sand, it does represent the forces that are being applied here. So note how you can see the sand that's been pushed up, and this has to do with the downward force that the foot places on as we ambulate forward. And of course, the sand does not apply the same amount of force, so we can see how we overcome that force that the sand provides and greater than that, and we get this kind of configuration. Now, when we look at these kind of forces, they can be somewhat negative. They can actually create injury. And we have to consider that these forces can result in problems. So any decrease in forces to limit injury will also decrease force in the opposite direction. So we always have to consider that, is that when we look at action-reaction, yes, you can decrease forces to limit injury, but can you also perform the task if you lower the forces that are occurring? The next thing we need to discuss are something called levers. When we look at the movement that occurs at bones of a joint, some things need to be taken into consideration again when we're trying to break things down. So we need to talk about something called levers first, and we'll talk a little bit how that relates to everything prior. So A lever is a rigid bar that can rotate about a fixed point when a force is applied to overcome a resistance. So think about, again, trying to move against something to throw or lift or so forth. Levers serve two important functions. First, they're required to overcome a resistance larger than the magnitude of the effort applied. So if you have a situation where you cannot create enough force to have the movement, you can use a lever to your advantage, which means you will need less force to move an object. You can also use a lever to increase the speed and range of motion through which a resistance can be moved. So for example, you can look at an old-fashioned bottle opener, a crowbar, a wheelbarrow, or a hand water pump. Each of these is a rigid bar that takes advantage of these laws of levers to make tasks or work better or easier. So when a force is applied to any of these, it turns about a fixed point known as a fulcrum, and it overcomes a resistance that may, in some cases, be no more than its own weight. So again, if we look at a wheelbarrow, right, we've got this fixed fulcrum, which is the wheel of the wheelbarrow. When we look at a hand water pump, we can see that there's a fulcrum where the movement occurs as the pump moves up and down. And again, each of these examples uses a small force to overcome a relatively large resistance in a short distance. So think of how much you can't lift as compared to how much you can put in a wheelbarrow to lift. Now, implements used in sports are levers that do the opposite, so such as a golf club, a tennis racket, a baseball bat, etc. When we look at these tools, such as a golf club, they use an extremely large range of motion to gain a great amount of distance at the expense of force. So when we think of swinging a golf club to hit a golf ball, it's not so much about the force, but about the speed. So again, using the advantage and understanding of levers, when you look at a golf club as it swings through the air with when the golfer is swinging the club, the longer the ball goes has a minor amount of force to require that, but where the real distance comes from is when a ball is struck in a golf course. It has to do with the speed of the club head as it's traveling through the air to make impact with the ball. So with those in mind, looking at anatomic levers, again, every bone in the body can be looked at as a rigid arm and therefore as a lever. The joint is the fulcrum or the axis of movement, and the contracting muscles are or is the force that's created. So we can see here in the diagram, doing a basic biceps curl, we can see there is a particular amount of weight here. Now it could be just the weight of the limb itself, or it could be something that's loaded in, such as a dumbbell. And our joint is the point of movement, in this case would be the elbow, and then the muscle is what creates the effort that moves the limb with the load towards whatever movement we're requiring. So in other words, we've got a lever here that's occurring just within the simple biceps curl. When we look at the particular arms of levers, we have to consider, what's happening and where. So we can see in this diagram here, we can see we've got a load at one end, so a box of weights, and we have an arm here that's running along, and we have a point here, in this case of a pyramid, and that point of contact is the fulcrum by which the arm will move about. So a lever arm is commonly defined as the portion of the lever between the fulcrum and the force points. So we have an arm from the fulcrum this direction, and then we have an arm again from the point of the fulcrum going in this direction. In this case, the load is on this arm to the left, so this is the load arm, and this other arm on this way is where the effort energy needs to be placed to cause the load to move. Therefore, this is the effort arm. So the effort arm is the distance between the fulcrum and the effort point. Okay, so we've got it sort of this long. And the resistance arm is the distance between the fulcrum and the resistance point. In this case, in this diagram, you can see that the load or the resistance arm, the load arm, is longer than the effort arm in this case. When we look at levers, there are three different kinds of levers that exist. So there are a number of arrangements that can occur between the 3 points of a lever: the movement or effort arm, the fulcrum, and the resistance or the load arm. So we can see here, this is your traditional teeter-totter. We have effort on one side of the fulcrum and load on the other. That is known as a first-class lever. We're going to talk about that in a moment. We can see another configuration here where the fulcrum is at this end with a load in the middle and the effort here. And then this other one, we have the effort now in the middle and the load on the far end with the fulcrum on this end. So let's do a first-class lever first. The axis or fulcrum lies between the effort and the resistance. Okay, so here between the effort and the resistance. The mechanical advantage here is looking for balance. It can also be used to magnify the effects of the effort or to increase the speed or range of motion on the basis of the relative lengths of the effort arm and the moment arm. So in so much as, we tend to show a first-class lever with the fulcrum at the midpoint and having an arm equal length on either side, this would give us balance. So in other words, if we were to put a 60-pound child on this side and we put a 100-pound child on this side, of course, this side, the force side, would hit the ground and the load would go up. We'd overcome that, and it's at balanced. We can also use it here as well when we're looking at the C-spine in relationship to, forward flexion of the head on the neck and the muscles in the back. We've got applied force here, so if the chin is down and we want to pull the head to go into extension and look up, our applied force here, in this case we'll just say is upper traps, for example. It's pulling down on the back of the skull here, causing the occipital region to go inferiorly. Our fulcrum is between C1 and the occiput, and we can see the resistance generally is gravity and the weight of the head that needs to be pulled back. So there has to be enough force back here to overcome the weight of the head and gravity to have us go into extension. So the examples I have here as well are the seesaw, the balance scale, and scissors. So flexion and extension of the head on the C-spine is an example of a first-class lever. Now, where's the resistance in this example and where is the load? As I said, the resistance is here anteriorly and the load is here posteriorly. So that is a first-class lever. A second-class lever has the resistance that lies between the axis and the effort. The resistance lies between the axis and the effort. The effort arm is always longer than the resistance arm in this type of lever. And just think of your wheelbarrow, right? You've got your fulcrum here with your load, and the arm is the force arm is much longer, right? So we see the effort arm is always longer than the resistance arm in this type of lever. This type of lever also magnifies the effects of the efforts so that it takes less effort to move the resistance. So you will, let's say you have 100 pounds in a wheelbarrow, you will be able to lift that 100 pounds in the wheelbarrow with less than 100 pounds of effort. Hence the reason why it makes it easier. So the wheelbarrow, a door, so this is the effort that's applied to the knob, and a nutcracker, for example, is also a second-class lever. A second-class lever in the body is a controversial topic among experts. Some feel that when the foot is being plantar flexed on a weight-bearing position, it is a second-class lever, with the fulcrum point of the ground contact. Effort is at the heel where the Achilles tendon attaches, and the force is the weight of the body. So you can see here again in plantar flexion, you've got your force that's being created here. Your fulcrum is the foot here at the metatarsal tarsal joints, and then the resistance is the weight of the leg itself. So you can see it as a second-class lever. The next one is a third-class lever, and in this case, the effort lies between the axis and the resistance. So you can see here, you've got the effort here in the middle, with the axis at this end and the resistance at the other. In this lever, the resistance arm is always the longer of the arms. So we can see here in this example, this is relatively long here to the resistance with the force in the middle. So the resistance arm is longer than the force arm. This represents the resistance arm, and this represents the force arm. A very small motion by the effort arm results in a large movement in the resistance. So this type of lever is for speed and range of motion, but it's not great at creating force. Okay, so we can see in the case here, Again, the biceps curl, our force here lies between the axis and the resistance. So again, the moment arm is this long, the resistance arm is this long. This is why it is the most common type of lever found in the human body. So the majority of levers that we find in the body are third-class levers because it's more about large range of motion and speed than it is to resistance. So we can see again, here's our first class, and you can see how, it works to a mechanical advantage here trying to move a rock. Our second class, its advantage again when its position can overcome less weight to have effect on the greater load. And then we've got this third class lever here, and the example here is a catapult, where you increase the speed here in the moment arm, and therefore the rock that's in the catapult can go further. So again, the most common lever that we see in the human body is the third class lever. So how does this all relate? Well, we need to do the principle of levers first. Any lever balances when the product of the effort and the effort arm equals the product of the resistance and the resistance arm. And this is considered to be the principle of levers. So you have balance when effort equals resistance. With this in mind, this allows us to calculate the amount of effort needed to balance a known resistance by means of a known lever, or to calculate the point at which to place the fulcrum in order to balance a known resistance with a given effort. So again, this is allowing us to calculate the amount of effort required to balance a known resistance, or it also allows us to calculate the point at which to place the fulcrum to find balance. So the principle itself is effort times effort arm equals resistance times resistance arm. Okay, so that gives us balance and no net movement. Effort times effort arm equals resistance times resistance arm. This principle also shows the importance of a lever arm length in determining the amount of effort needed to balance a given resistance. If the effort arm is lengthened while the resistance times the resistance arm remains constant, the amount of effort required to balance must decrease. If the resistance arm increases, the effort must increase. So this is about recalculating what's happening here. So you can see that in the case of this individual who's wanting to move a very, very large rock, by placing the fulcrum closer to the object and really lengthening the moment arm or the movement arm, it takes a lot less effort to move the rock as compared to if this individual went up to the rock and tried to move it directly. So we say that, if the resistance arm increases, the effort also has to increase. This results in a third class lever requiring more effort than the resistance that they must balance or move. So this is, again, when we look at third class levers of the body, again, it's not about creating resistance, it's about speed. When a lever has an effort arm longer than the moment arm in first or second class levers, it's said to favor force. And we can see it here, of course, the longer the stick, the less effort to move the rock. Make the effort arm longer, the work becomes easier, but the speed and the range are significantly reduced. So you give up one for the other. A lever whose resistance arm is longer, whether a first class or a third class lever, favors speed and distance. So when we look here at the diagram with the golfer, we say the golf swing lengthens the anatomical arm, and therefore it lengthens the resistance arm, which results in increased speed and range. Remember, the larger the range, the more speed. So when we look at the golf swing here, the fact that we can take it through a much greater range, because remember that the club is the extension of the movement, so we have to take into account not only the length of the arms, but also the club itself. You can see the amount of range that has occurred here at the head, because it's the head that's going to make contact with the ball. The larger the range that occurs in the swing, the faster the club head will move, and the faster it's going, the longer the golf ball is going to travel upon impact. So why all of this to massage? It seems complicated, but really isn't. But why do we need this for massage? Well, this all has to do with REMX. When we're prescribing remedial exercises for our patients, we do really have to keep in mind in terms of what's required in the task, what's happening, and in some cases we have to keep these levers in mind and some of these other principles. Next, interpreting assessment results. So when we look at assessment results, and we want to determine many things, even what muscles we need to lengthen or strengthen or work on, or what joints do we need to work on. All of this is based on, taking these kinesiology considerations when we're interpreting the assessments. Functional abilities evaluations, and I've said this to you guys before, I've talked about it, but this also helps us in creating increased ability for the client to perform whatever it is they need to perform. And remember, it's not unusual that the individual will hurt themselves, whether it be at work or at home, if they're not able to overcome some of these forces and so forth when they're trying to perform something that they're not prepared for. Understanding activities of daily living, of course, that goes hand in hand in it. One has to determine what's being done in their activities every day, and considering it from the perspective of levers and forces and so forth. And interpreting functional requirements. So they may come in and say, this is what I need to do. I lift from here to here, and the box usually weighs this much. And you have to be able to interpret that again in terms of creating remedial exercises, or also maybe, as we said earlier, understanding that maybe the forces are being applied in the wrong direction by the patient, and we need to better suit those forces to make it work better. In other words, less violation of the laws. Thanks for listening to this slide set. One more to come. Have a great rest of the day. Thanks.